Let me first thank the organizers for the invitation. And I'm going to talk about work I did recently-ish. And it's a funny story because I was trying to do something else. And it didn't work. And then I went to a talk in number theory and I heard about Hecke pairs. And I understood I could do something about this. So that's how I did it. And so I tried to plan a talk for students, so with little exercises maybe. So don't hesitate, students, don't hesitate to interrupt me. And yes, older people, more experienced people, be nice with the approximation I will be making and the lies I will be telling. So the main motivation is it's a stability result for the Baum-Connes conjecture. So let me first establish notations. So in all my talk, I will talk about an inclusion of subgroups, lambda inside gamma. And this will be a discrete and countable groups. Countable. Okay. Also, everybody probably knows that you have the regular representation that's defined on L2 of gamma in this way, and that we denote by C star radius of gamma the closure for the norm of the span of these regular representation operators. And so here's my first approximation, not really, but if you have a Banach algebra, a complex Banach algebra, of course, you have K-theory groups, and so here's a very fast way to define it, but there are a lot of theorems behind. Okay, it's, you can take the homotopy groups of GLN of A and take the limit. Maybe I should define like this. Okay. So you embed each GLN of A inside GLN plus 1 with the top left corner, and you add a 1 at the last coefficient. And you look at the homotopy groups of these things. And actually, there is a very deep theorem of Bott which says that these homotopy groups are periodic, so you only have 2 of them. So you have K0 and K1. Okay, so K1 is the connected component of GLNA, and K0 is the pi 1 of GLNA. Okay, when n gets bigger and bigger. Okay, so that's a very fast way to define it, but okay. And it's a very important group. So these are called the K-theory groups. These are abelian groups. And they are very important in a lot of parts of operator algebras, but also in other parts of mathematics. And the problem I'm interested in today is goal. It's compute the K-theory groups of the reduced C-star algebra for discrete group, for instance. And for this, there is a very famous conjecture, which is called, which was enunciated by Baum-Connes. So I just asked George, and he told me it was really, the birth of the conjecture was in Kingston in July 1980, Kingston. Okay, and you have you have 2 papers from the 80s, in which you have first a paper of Baum-Connes with a first version of the conjecture, let's say, and then you have the modern formulation of the conjecture with Baum-Connes and Hecke. Okay, and what is it? It's following. So they define a map that takes value into the K-theory groups of which I'm interested in. And here you have some group here. So this is called the assembly map. For gamma. And the conjecture is that the assembly map is an isomorphism. So I will put quotes to say that it's a statement. Okay. And the point is that the left-hand side, so it's called the analytic k-homology, the k-homology. And this is supposed to be computable by tools of classical algebraic topology. So that's a classical algebraic topology tool. So for instance, to illustrate what I mean, because when I was a student, I always heard people saying that, but they never say why. So I will give you one argument at least. So for instance, if gamma is a torsion-free, and the classifying space is a CW complex of dimension less than 2, k top gamma, so it will just be the homology, the integer homology groups of gamma.
So it's BW, B gamma?
Sorry?
You say BW, it's
oh,
B
mince.
gamma?
Yes, B gamma. I think that's it. I think you can even do 3 and then put H3, but I'm not sure anymore. But so for low-dimensional groups that are torsion-free, the k-homology is given by homology. You see, so that's really an algebraic, a usual suspect in algebraic topology. Okay, but you can compute. Okay. Also, I wanted to. I'm slower than I expected, so I will not go into more details. But mu gamma, it should be thought as an index map. So here, the people living here, they are kind of generalized elliptic operators living on space with a proper action of gamma. And yeah, so it's like taking the index of a operator, whatever that means. And okay. And yes. So this conjecture has a lot of consequences. So I will denote it by so remarks. So the conjecture has lots of applications. So all over mathematics, in analysis, in algebra, in topology, I will be mainly interested in topology today. But you have the idempotent conjecture of Kaplansky that follows from surjectivity. Okay, you have other, but I'm kind of blanking. Okay, but one of them is the Novikov conjecture. So which follows from the injectivity of the map. Okay. So the Novikov conjecture is long to explain. So it states that the higher signatures are homotopy invariant. Let me tell you of another conjecture, but which is stronger and which is, I guess, easier to understand. It's the Borel conjecture. And the Borel conjecture, it implies the Novikov conjecture. And people say in topology that the Novikov conjecture is a local version of Borel. And what does it say? It says that, so the Borel conjecture, it says that if you have aspherical manifolds are rigid, so if you have a manifold with all homotopy groups which are trivial but the pi 1, it should be that, so an equivalence, homotopy equivalence between aspherical manifolds should be homotopic to a homeomorphism, okay? So for instance, hyperbolic manifolds from Mostow rigidity theorem, they satisfy the Borel conjecture. Okay, so this is a big thing, and I think that's one of the main applications of the Baum-Connes conjecture is to prove the Novikov conjecture, because so maybe I'm wrong, but I think algebraic topologists, they were only able to prove it for virtually abelian groups before. And now the Novikov conjecture is available for all groups which have a coarse embedding into a Hilbert space, which is a much more a bigger class, because I don't think we have a lot of examples that don't do this. Right? Okay, so that's the first thing I wanted to say, and I'm almost done with remarks like this. Yeah, so there is a version of a I will need this for later in my talk, a version of a conjecture with coefficients. So it means that if your group gamma acts on a C-star algebra, you have another assembly map. This time it's to compute the value of the K-theory groups of the reduced cross product of the C-star algebra. I will not define this. Just think of A as being the C and this map, if you don't know what it is. And the Baum-Connes conjecture with coefficients is that this map is an isomorphism for all coefficients. Okay. Yes. Okay. And so the conjecture holds for large classes of groups already. So all groups with the H group property so this is X and Kasparov. And also Jean-Louis Tu. I think it's around 2001. No, okay. Maybe 2000, je sais pas. Mais non, it's okay. Xn Kasparov, c'est 97, ok. Hop, merci. So for instance, all amenable groups, they have a group property. Let's say Gromov hyperbolic groups. This is Laforgue, Vincent. And also I will state two results which I need, which are stability results. So if you have a normal subgroup in gamma, and Q is the quotient group, then the Baum-Connes conjecture for the normal subgroup, let's say with coefficients, so I add a C here. So it's stable by extensions.
The coefficients for the quotient.
Sorry?
The coefficients are for the quotient.
Yes.
It's a cross product with the quotient.
Yeah, but you also need...
Well, at least you know. Okay.
Yeah, but you also need the Baum-Connes conjecture for all subgroups which have finite index, which n is finite index in, and so that's better to... So otherwise, I have a statement that's longer, and I want something quick. And Lastly, so if gamma acts on a tree, metrically, by isometries, then if all the stabilizers satisfy Baum-Connes with coefficients, I will gamma stab then you have a Baum-Connes conjecture for gamma. So same thing, you have a more precise results with coefficients and everything. I'm just going faster so you can understand. And so what I have is what I will prove is a kind of combination of the last two results. And then I stated these ones just to show you how we can build interesting examples using the result of extension I will tell you about to prove interesting examples. But these are not the only groups that we know that satisfy the conjecture. There are other classes of groups. Interestingly, here in Gromov hyperbolic groups, you have some groups with property T. So it's kind of orthogonal to having a H-group property. So you see. And no non-counterexample is known for complex coefficients, so for the original statement of the conjecture. Okay. So are there any questions from the students? No. Okay. So I want to recall a little bit things about the H-group property. And coarse embeddings into Hilbert spaces, so which I will denote by CEH. And let me remind you what is a coarse embedding. So here I will always be interested in a metric space. I will take it to be a discrete, countable, and of bounded geometry. So think it's a little bit more than locally finite. It means that the cardinality of the ball is uniformly bounded. Okay, for every R. Okay, so think of a graph, and you have it's a regular graph. Okay, every vertex has less than 13 neighbors, or D neighbors for D fixed. Okay. So we say that a metric space like this is coarsely embeddable into a Hilbert space if there exists a map psi from X to H. H is a separable Hilbert space such that so you're allowed to distort the distances. But you have to respect what is bounded and what goes to infinity with two control functions. So here my functions rho plus and minus, they're positive functions over the real, and they are increasing and proper. Okay. So you know this when rho plus and minus are affine. You know this notion as quasi-isometries. Okay, so if you take AX plus B, then here you say that X, this is a quasi-isometric embedding into H. Okay. Here we allow something much more interesting, much more flexible. So the basic example, it's that of a tree. Example, X is a tree. Bless you. Up. Okay, a tree. And yeah, so exercise for the student. You look at, you just fix a vertex V naught. And then what you do is, so you look at H, which will be here. Can I take L2 of V? I guess. No, I fixed V0, it's okay. Of X. And what you do is, if you have a vertex, you just, let take the L2 of the edges, and I will sum the Dirac function in L2 over the unique geodesic going from V to V0. Like this. Okay. And you can check quite easily that here, rho plus or minus, you will take it to be R, the square root. Okay. So you will. It's an exercise for students. So you use that you have only one arrow. So if you take 2 points, then if you take the difference, it will have only the people on the geodesic will live. All the other will be killed by the difference. Okay. Okay. So here you have a concrete coarse embedding, which is not a quasi-isometry. Yes. And the space I'm interested in. Which one is it? So here, x will be, so recall from the beginning of the talk, I have a quotient, so I take a subgroup, I take the quotient, coset space, and on gamma, let's say that I have a finite generating set, and I have the word length. Okay, so I count the number of generators to pronounce a word in gamma. And from this, I define a metric on x. So I just take, so these are two cosets, and I just take so I have a distance on my group, so it's the distance of the Cayley graph. Okay, if I have a word, I count the number of generators. If I have 2 points, I count the number of generators of s minus 1 t. And here I will do the same. So now I have my metric space and I have cosets. And I just take the distance in this metric space. Okay, so this is just the inf of, so let's say x, y, okay, for x belonging to s, to each coset. So this is also that. Okay, meaning this is a set, and I take the inf of the length applies to this set. Okay. So yeah, together. And maybe an example. Here, if gamma is F2, so I have the generators are A, B, and their inverses. Okay. And what do I do? So I will up like this. What I can do is, are there colors? Yes. Let's say that I take the cosets of the subgroup generated by A. So it means that my cosets are all the horizontal lines, like this. Okay. And so you see all these cosets, they have distance 1 between each other. Okay. And so the questions, the first, yeah. So that's a fact, okay. So this is my example. I will keep it because after that I want to say something about this. And so now I can tell you the main theorem, which is the following. So so you have a subgroup such that this space, so the coset space with this distance I just defined, admits a gamma equivariant coarse embedding into a Hilbert space and such that the Baum-Connes conjecture is true for the subgroup, then the Baum-Connes conjecture is true with coefficients for the big group. Okay. So of course I have more precise statements with actual coefficients and everything, but this is the fastest way to describe it. And one corollary, which is interesting to me. Okay, now I have to say something. So if I take a subgroup which satisfies some condition, such that the subgroup and the coset space are coarsely embeddable into Hilbert space, then the Novikov conjecture is true for gamma. So here, what is this symbol? This symbol is actually, I need my subgroup to be almost normal. So that's my the thing I want to talk about after this. So I should have defined before, but too bad. So the thing is, if you have an equivariant coarse embedding into a Hilbert space, it's automatically, the subgroup is automatically almost normal. So I don't need to talk about that before. But here I relax. So here I only have properties about metric spaces, so it's not about the... And it turns out that being coarsely embeddable into the Hilbert space for the coset space doesn't always imply that you are almost normal. So I need to precise this now. Okay. And also you should know that these kind of things here, you have examples of groups like this, such that the total group gamma is not coarsely embeddable into Hilbert space. These examples were constructed by Arantseva and Romain Teixeira. Okay, so for instance, now you know that this example, it satisfies the Novikov conjecture. Maybe I should say that this answers the question of Guoliang Yu. He asked if he has actually the question for normal subgroups. So now it's a little bit, for a little bit more work, you can have the answer for actually not even normal subgroups, just almost normal. Okay. And here, what should I say? So this is kind of a mix between 3 and 4. Here, 4 is hidden, and I'm not tall enough to lift. Okay. So it's a stability result, but here you don't have an actual quotient group. Okay. So, what is an almost normal subgroup? So it's also called a Hecke paire. And it means the following. It means that any two conjugates of my subgroup are commensurable, which means they contain a subgroup of finite index. And here, what you can do is just take the intersection of this. Okay. Yes. And you can see it in a lot of different ways. For instance, it's also true that this means that my metric space, my coset metric space, is of bounded geometry, so it's equivalent to it being locally finite. It's also yes. And it's also equivalent to if you take lambda orbits on the coset space, they are finite. Okay. So this kind of inclusion of subgroups were first used by Shimura a long time ago, and they were really popularized in operator algebras by the work of Bost and Connes, which use them to define the Baum-Connes system, which is very famous. I guess everybody knows this. much time? I have 45 minutes, right? Yeah, it's still 15. Okay. So, yeah, my example of the free group on the left board. So you see this is not an almost normal subgroup, right? As I told you, all the horizontal line that I drew like on the right side, it's at distance 1 of the horizontal one corresponding to just the subgroup generated by A. And you see that I have as many as I want, so it means that the ball centered at this line contains many, like the ball of radius 1, it has infinitely many elements, so it's not locally finite, so it's not a Hecke inclusion. Okay. Yeah. So maybe some examples. Where was I? Okay, I don't know, I will continue here. Examples. So of course you have so normal subgroups, and also if n or the index is finite. So all of these are almost normal, trivially. And you have more interesting examples, such as the original one from number theory, which you take a SLN Z, for instance, and it's almost normal in SLN Z 1 over P, where P is prime, or P doesn't have to be prime, actually. And it's also almost normal in SLN Q. Okay? And in that case, the one in Z 1 over P, if you take the coset space, it's the P plus 1 valent tree that you get. Okay. So that's a nice fact. Okay, so what do I have time to say actually? Going way too slow. Okay, I will tell you directly the secret to prove such a theorem. The main tool for the proof. It is a quotient, a general, yeah, a quotient. A quotient group for Hecke pairs, which is called the Schlichting completion. Okay. And what you can do is the following: you take gamma, and you take the permutation representation on the coset space, and this you endo it with the pointwise topology of pointwise convergence. And for this, it's a totally disconnected group. And okay, so let's call this phi. And you define the Schlichting completion. It will be, you take the image of gamma and you close it for the pointwise convergence. And this you can always do, but actually what it happens is that when the subgroup is almost normal, this is a locally compact group. Okay, so when this is a TDLC group, totally disconnected, locally compact group, when the inclusion is almost normal. Okay. To see this, you just look at lambda, then this, what does it do? It's a subgroup of a permutation that are supported on lambda orbits. Okay. But I told you that being almost normal, it means that my lambda orbits are finite. And so I have a product of finite permutation groups, so it's a compact group. So already you know that this guy is compact, and then you just need to show that the closure of the image of that guy, so it's compact and it's open. And this is just because you can describe it as the stabilizer of the point, which corresponds to like the coset lambda. Okay, that's a general fact. If you didn't understand, just forget about it. So the point is, now you have a replacement for the quotient group, and it's a totally disconnected locally compact group. And with this in mind, by kind of adapting the proof of the extension result I told you about, so it's not that easy, but it's doable. And so you prove that if lambda n g satisfy the Baum-Connes conjecture with coefficients, then you can go back to gamma. Okay. The thing is, you can see directly that if the coset space gamma over lambda has a gamma equivariant coarse embedding into a Hilbert space, this is completely equivalent to G, so the Schlichting completion being having the H group property. Okay, so in this I just stated the results I need, but what you can get from that is that if you want to study a Hecke pair, now you have a way to any metric property of the Hecke pair is a metric property of a Schlichting completion. But better, any equivariant metric property on this metric space, it will be equivalent to a group property on the Schlichting completion. For instance, if the space has an equivariant property A, it will be, of course, the same as G, the Schlichting completion being amenable. So you have a dictionary between properties of a space and properties of a group. Okay, and yeah, so I'm almost done. So I will not. I wanted to talk maybe about proofs and such things, but it was unrealistic. So I can tell you a little bit about examples because. So what kind of example do you get? So what can you prove? So examples of so let's take a irreducible lattice inside a product GA-GT, where GA is a TDLC group and it has H group property. And GT is a non-compact group with property T. Locally compact. Yes. And what you can do is, if you now for any subgroup compact open K inside a GA, if I denote phi being the projection onto GA, so it's an irreducible lattice. It means that this projection, it has dense image, and then you can take the inverse image of K, and this will be an almost subgroup in gamma. Okay. And so if you know the Baum-Connes conjecture with coefficient for this guy, then you know it. And for GA, for instance, if GA, yeah, here you know it for GA, so you will know it for gamma. Okay, so such a group, if you just know the conjecture for lambda, you will know it for gamma. Okay, and the main example, for instance, you can take an algebraic group over Q, so such that the R points, it will be SPN1, for instance, so it has property T, and the QP points, it will be H group. Okay, so of rank 1, for instance. So this is possible, and then, sorry, so what you will have is that the Z points, the integer points, there will be you can find such a G such that it's a uniform lattice inside GT, so inside SPN1, so it's hyperbolic, and so you know that the Baum-Connes conjecture holds for that group. And such that GA is a H group, so that you can prove that the Schlichting completion, basically it will be GA quotiented by a compact subgroup, so it will also satisfy Baum-Connes. And so then you have that the 1 over p points of your group satisfies the Baum-Connes conjecture with coefficients. So you have to restrict n to being 3 and 5. Because if n becomes too big, then the rank of G of the QP points is not 1 anymore. But if you look at the classification of algebraic groups over local fields, you can find such groups. And you probably have more examples. You can play with any number of factors in your product and things like that. And probably you have examples that do not come from algebraic group, but I told you I had this. It's by going to a number theory seminar that I've heard things like that. So yes. So do I have time? Oh, I still have 3 minutes. So this is what I already did, and I said in my abstract that I want to say things about things I'm currently doing about this. So natural question is that you want to compute maybe the K-theory of Hecke C-star algebra. So Bost and Kohn, in their paper, they define a C-star completion of the algebraic Hecke algebra with complex coefficients. And the thing is, you want to think of it as the analog of the C-star algebra of your group, of your quotient group. And so you can actually define an assembly map to compute the K-theory of the Hecke C-star algebra. And the question is it an isomorphism? So the thing is, if you have a gamma equivariant, so what I want to prove is, when you have a gamma equivariant coarse-embedding to Hilbert space, meaning when the Schlichting completion has a group property, then the assembly map is an isomorphism. I'm not there yet. I think it's quite doable to prove that it's injective if the coset space has a coarse embedding into Hilbert space. But the equivariant part is, for now, I'm still working on this. Yeah. So I will stop here, and thank you for listening to me.
Are there any questions?
The Hecke completion is the C-star algebra of the Schlichting group cut by the projection.
Yes, it's a corner of a Schlichting of a reduced C-star algebra of
maximal reduced.
And yeah, I don't think there is any way to actually compute a corner of an algebra if you know the K-theory of the algebra. But yeah. So in that case, you can also say that it's a kind of, so you see that gamma over lambda, it's also G over K, where G is the Schlichting completion and K is the closure of lambda. Yeah. It's a proper G space for the G, the Schlichting completion. So you can talk about the equivariant row algebra. So X, the coset space, it has an action of G, and it's a proper space. And so it actually, you can compare the row algebra with the Hecke algebra. That's kind of what I'm doing. And then you can also try to make a groupoid picture.
But yeah, just the corner algebra is Morita equivalent to an ideal. Maybe.
Yes, but I don't really know how to relate this ideal to anything. Yeah, trying to use cones.
Do you know what the quotient looks like?
A quotient? With the ideal? No. I mean, no, I don't really know. It's the ideal generated by the projection.
You should take the quotient.
Even at the von Neumann algebra level, it's hard to determine the central support of this projection. So it can be everything, it can be proper.
Yeah, usually it's not everything.
Yes, usually it's not everything. Is there any other question? No? Then thank you again.
Yes.